Hello, this is the fall presentation for the Zebra RFID Capstone design team. Our team is led by our technical directors, Joe Morera, an engineering fellow, and Jean Hoffer, a director of systems engineering at Zebra. Our team consists of myself, Remy Lloyd, an electrical engineering student, and Ryan Hurley, also an electrical engineering student. The motivation for this project is improving Zebra's UHF passive RFID wristbands, which are primarily used for monitoring patients' movements in hospital settings. The anticipated best outcome for this project is to provide Zebra with an understanding of the behavior and limitations of their current wristbands and to develop alterations and prototypes which provide a documented improvement in performance.
The team focuses on research and development of RFID, material composition, and statistical analysis. The research and development is on passive ultra-high frequency RFID. This means no batteries are used for the RFID. All the energy used to send the information in the RFID tag comes from the antenna. The material composition matters quite significantly. Humans have a very high water content, and this is known to absorb RFID. Through the use of spacer wristbands, we can get around this by separating the tag from the wrist. The polar plot in the bottom left is with a spacer wristband, and the top right is without one. The bottom left one is preferred as it's almost uniform, this meaning any rotation of the wristband will still provide accurate readings. The readings were taken over a period of 20 seconds. If you compare to the top right graph of just the wristband on the wrist, it only works during that top right section where the tag is facing the antenna. So rotating the tag on the wrist, or if the person turns around, will no longer allow it to read. But the implementation of a spacer wristband will allow for this improvement. Our team focuses a lot on repeatable testing and accurate procedures. We test different times each day and over different periods of time, so we need to make sure everything gets set up the same way every single time to allow for repeatable testing. There is quite a significant economic impact. Improving the range will reduce the number of antennas required. So for example, if the range is quite small and an antenna is needed in every room and multiple times in the hallway, the number of antennas would be reduced if the range of each tag was further and less antennas would be needed. This would consume less power and reduce the number of installations, greatly reducing the cost. For Zebra, we could potentially reduce the cost of producing each tag, either through materials or new designs, and this would drastically snowball as over 300 million units of these are produced yearly. Finally, the combination of the first 2 points allow for overall more affordable RFID. This will hopefully allow for more hospitals and other technology to start using RFID, and in the hospital case, potentially saving lives. Our testing setup involves using Zebra software on a personal computer. This connects to the RFID reader. This communicates data of the number of times each tag is read, and we set this to a 20-second interval. The reader is connected to an antenna. It supports multiple, but we have been testing with just one, and over the air this communicates to the tag. A tag can be seen on the right. The lower one is an RFID tag. It has a 3D printed spacer right here. This allows for repeatable testing, and the intended tension is a 2-finger gap. So it's roughly about the same size as a 2-finger gap and allows for repeatable and accurate testing. There's a little dot on here which we use to test the angles, and the wristband on top does not include RFID, so it won't interfere, but we use it to mark the angles without needing to draw on top of the arm. This way we're able to rotate and receive the data from the antenna through the reader into the computer, and we do a bunch of analysis and plotting to produce the results.
At this stage in the project, my technical contributions have consisted of RFID research and baseline testing of Zebra's current RFID wristband, as well as baseline testing of Zebra's current wristband when paired with various attachments such as the Comfy Cuff and the Fabrifoam Nimbus Comfy Cuff. In the future, my technical contributions will be focused in creating prototypes and testing those prototypes to compare to the testing of the current wristbands.
My technical contributions include RFID research and development. This is focused around the materials, technology, and equipment we have. This led into baseline testing. We tested 10 tags at 24 different angles total, and this produces a plot on the right. This is what rotating the wristband looks like. The dot on the wristband, which is found here, is where the tag is. When this is facing, it is at an angle like this, and it has a very high performance. When the tag is on the back of the wristband, the performance does not read or is very, very poor. So our goal is to reduce this and improve the performance at much more ranges. We did this by using a spacer wristband. This provided a near perfect circular plot, which was a drastic improvement. My next focus was keeping the testing repeatable and accurate. I tried to track as many variables as possible and make sure that through different testing sessions we were able to set up everything in the exact same way and make sure that testing was as repeatable and accurate as possible. My future accomplishments revolve around antenna designs. Here is the current antenna design. It consists of two poles with a loop, and the chip is found on this little line in between. We have a metallic thermal printer, and this allows us to print new antenna poles. So we will test and design different material configurations, different antenna designs, and we will use the same testing methods we have to compare the performance to what we have currently. We can also implement different materials. So for example, we could test really conductive materials like copper or silver, which could have a much bigger benefit. We could also test different spacer materials. So here is 3 examples we have tested with varying materials and thicknesses. Using our existing method, we can compare our future developments to our baselines that we've just done. This way we can see how our designs compare to existing technology. Hopefully we'll be able to improve this without using spacer wristbands. We've already proven their significance. However, we'd like to see if we could achieve the same result without requiring someone to wear 2 wristbands at the same time. A quick overview of our future accomplishments. We are going to print new antenna poles and new antenna designs. We will compare these to our existing baseline. Our goal is going to be RFID improvement over a wide range of angles without requiring an extra spacer wristband. We're going to be able to compare each one of these to the existing methods to find the one with the highest performance. We are able to test different antenna configurations, materials, and other ideas that we come up with along the way. We're not limited to just changing the antenna configuration, for example. We have a few notable risks. The first one being testing repeatability. It's important that we can get the same results in different environments and different situations. RF interference is quite important as you can't see it, but it's obviously always there from other devices and electronics in the room. Finally, tag deterioration can happen when we overuse testing a single tag. In order to avoid these risks, we make sure we track every variable accurately. This allows for repeatable testing, and we monitor the environment to make sure there's no extra RF interference. Anything that could be interfering, we usually lock up in large metal containers to make sure they don't interfere. Finally, we make sure not to overuse testing a single tag to make sure they don't deteriorate or reduce in performance over time. We would like to thank our program director, Dr. Sunak, as well as our technical directors, Joe Moreira and Gene Hofer, as well as everyone at Zebra who has shared their experience and advice with us along the way. Thank you.